Look up tonight, not with a telescope, not with any instrument at all, just your eyes, just the naked and ancient act of tilting your face toward the dark. What you see, if the sky is clear and the city lights are far enough behind you, is a scattering of pale fires against a field of black. You have probably looked at this scene your entire life and understood it, without thinking too carefully, as a picture of fullness, stars everywhere, light in every direction, the universe spread above you like a ceiling decorated with burning things. That is the instinct. That is the story the sky seems to tell. And it is, in almost every meaningful way, wrong. What you are actually seeing when you look at the night sky is not the universe. You are seeing the exceptions. You are seeing the rare, improbable, temporary places where matter gathered tightly enough and burned hot enough to produce light that could cross the distance to your eyes. The darkness between those points of light is not a backdrop. It is not the canvas on which the stars are painted. The darkness is the dominant fact. The darkness is what the universe is mostly made of, and the lights you are counting, those few thousand stars visible to the unaided eye, are something closer to an accident than a rule. They are the outliers. The universe did not make them because it tends toward brightness. It made them in spite of a deep and overwhelming tendency towards something else entirely. This is where the journey begins, not with the stars, but with what surrounds them, not with the light, but with the architecture of the dark. And if you are new here, stay with us at Beyond the Universe, because what we are about to trace together is not a tour of the cosmos as it is usually presented, not a celebration of its scale or its beauty or its strangeness, but a slow and careful descent into the realization that the universe is not what it appears to be from the ground. It is colder, emptier, and more indifferent than the night sky suggests. And the deeper you go into the science, the harder it becomes to look up and feel the same way you did before. If that means something to you, if the weight of what you have seen here is something you want to carry further, subscribe to Beyond the Universe. Begin with something simple. Begin with the act of breathing. Right now, wherever you are, the air around you is dense with matter. Billions upon billions of molecules are colliding with your skin every second. The ground beneath you is solid, packed with atoms arranged in crystalline and molecular structures so tightly bound that you cannot push your hand through them. The world you inhabit is, by the standards of the cosmos, extraordinarily crowded. Matter is everywhere you look. It fills your body, your room, your city, your planet. And because this is the only environment you have ever known, it is easy to assume that matter is the default condition of reality, that things exist, that space is filled, that the universe at its core is a place of presence. But step back far enough, and the density you take for granted dissolves almost immediately. The distance from the Earth to the Moon is roughly 384,000 kilometers. That gap, which feels enormous from a human perspective, is almost nothing on cosmic scales, a hair's width on a map that stretches to incomprehensible distances. Between the Earth and the Sun, the space is not empty in the absolute sense. It contains thin streams of charged particles flowing outward from the solar wind, occasional dust, the faint traces of the interplanetary medium. But it is, for all practical purposes, a near-perfect vacuum, a volume of space so large that it would take light over 8 minutes to cross it, and yet it contains almost nothing you could hold or weigh or feel. Now extend that thought outward. The nearest star to our own sun is Proxima Centauri, sitting at a distance of approximately 424 light-years. That number is so large it resists intuition. Light, which crosses the distance from the Earth to the Moon in about 1.3 seconds, takes more than 4 years to travel from our sun to its nearest neighbor. If you were to shrink the sun to the size of a grapefruit and place it on a table, the nearest neighboring grapefruit on that same scale would be roughly 2,500 kilometers away. Not across the room, not across the city, across a continent, and between those two grapefruits on that scale, there would be nothing. No air, no dust, no particles of any significance, just the geometry of distance, stretching in every direction, uninterrupted. This is the texture of the universe at the stellar scale. Not crowded, not full, mostly nothing, with occasional fires burning at distances so vast that the fires themselves are invisible to each other in any meaningful physical sense. The stars in our galaxy, all several hundred billion of them, are separated by averages of several light-years. The Milky Way, which contains more stars than there are grains of sand on all of Earth's beaches, is not a dense cloud of burning matter. It is an almost unimaginably thin disk of gas and dust and stars, most of which are separated from their neighbors by volumes of space so large that the word empty barely begins to describe them. And yet, even this, Even the scale of the galaxy is not where the emptiness becomes truly disturbing, because the Milky Way is not alone. It is one of an estimated 2 trillion galaxies in the observable universe. 2 trillion. And those galaxies are not evenly distributed through space like raisins in a loaf of bread. They are gathered into clusters and superclusters, strung along filaments of gravitational influence, arranged in a vast and intricate structure that cosmologists call the cosmic web. And between the strands of that web, between the filaments and the walls and the clusters, there are regions of space so large, so dark, and so nearly devoid of galaxies that they challenge every intuition you have about what the universe is supposed to look like. These regions are called cosmic voids, and they are not anomalies. They are not gaps in the data or errors in the map. They are fundamental features of the large-scale structure of the universe, and they occupy a staggering proportion of its total volume. Some voids span hundreds of millions of light-years across. Some are even larger. The Botas void, one of the most studied of these regions, stretches across roughly 330 million light-years of space and contains, within that enormous volume, only a handful of galaxies where there should, by the surrounding density, be many hundreds. It is not a hole in the universe. It is a chamber, a vast, dark, nearly silent chamber in the architecture of the cosmos, and it is not unique. Voids like it exist throughout the observable universe, and together they account for the majority of the universe's total volume. Let that settle for a moment. The majority of the universe's volume is occupied by regions where almost nothing shines. The filaments and walls and clusters where galaxies gather, the places that look in the famous deep-field images from our most powerful telescopes like glittering webs of light, those structures are the minority. They are the thin, bright edges of something much larger and much darker. The voids are not the spaces between the universe. The voids are most of the universe, and the galaxies, the stars, the planets, the life, all of it exists in the narrow margins, the compressed edges, the thin, luminous skin stretched over an interior that is, by volume, almost entirely dark. But it goes deeper, because even the images that seem to show us a universe full of galaxies are deceiving us in a specific and important way. When astronomers point a telescope at a patch of sky and collect light for hours or days, the resulting image compresses an enormous volume of three-dimensional space into a flat picture. What looks like a dense field of galaxies is actually a column of space stretching billions of light-years in depth, and the galaxies in that image are separated from each other by distances that the image cannot convey. The Hubble Ultra-Deep Field, one of the most famous astronomical images ever taken, shows approximately 10,000 galaxies in a patch of sky, roughly 1/13 the diameter of the full moon. It looks crowded, it looks full, but those 10,000 galaxies are distributed across a volume of space so vast that the average distance between neighboring galaxies in that image is measured in millions of light-years. The image is not a window into a full universe. It is a compression of an almost incomprehensibly sparse one. This is the first contradiction that the universe forces on you when you look carefully enough. The sky appears full because your eyes are sensitive to light and insensitive to distance. You see the photons that arrive, but you do not feel the void they cross to reach you. Every star you see at night has been broadcasting its light across years, decades, centuries, or millennia of empty space just to deposit a few photons on your retina. The light is real. The journey it made is real. But the space it crossed, that is the part the sky hides from you. That is the part that changes everything. Consider what it would mean to actually travel through the universe rather than simply observe it from a fixed point. Imagine leaving the Earth and accelerating outward, not at the speed of any rocket we have built, but at the speed of light itself, the fastest that any signal or object can travel through space according to everything we currently understand about physics. At that speed, you would cross the distance to the moon in about 1.3 seconds. You would reach the sun in just over 8 minutes. You would reach the edge of our solar system, roughly at the boundary where the sun's influence fades into the interstellar medium, in somewhere between 1 and 2 days. And then you would enter the interstellar void, the space between stars, and you would travel for 4 years before reaching the nearest other sun. 4 years at the speed of light. 4 years of crossing nothing. No planets, no asteroids, no significant concentrations of matter of any kind. Just the thin interstellar medium, a gas so diffuse that it would be considered a near-perfect vacuum by any laboratory standard on Earth, and the faint, ancient light of distant stars arriving from all directions, growing no brighter as you move, because the distances involved are so large that even traveling at the maximum speed the universe permits, you are barely moving on the scale that matters. And this is just the distance to the nearest star. The Milky Way is roughly 100,000 light-years across. To cross our own galaxy at the speed of light would take 100,000 years. And the Milky Way is one galaxy among 2 trillion. The nearest large galaxy to our own, the Andromeda Galaxy, is approximately 2.5 million light-years away. 2.5 million years of travel at the speed of light, through a void that contains almost nothing, to reach the next island of stars. And Andromeda is our neighbor. It is on cosmic scales practically adjacent. Beyond it, the distances grow in ways that the human mind was not built to process. The nearest galaxy cluster beyond our own local group is tens of millions of light-years away. The nearest supercluster is hundreds of millions. The edge of the observable universe, the farthest distance from which light has had time to reach us since the universe began, is approximately 46 billion light-years in every direction. And across that entire volume, the matter is arranged in those thin filaments and walls, with the vast majority of the space occupied by the dark chambers of the voids. You are not living in a full universe. You are living in a universe that is almost entirely empty, with a thin and fragile web of matter stretched across it like frost on a window, beautiful from close-up, but vanishingly thin against the cold glass of the dark. Now consider what it means that we can see as much as we do. The fact that the night sky contains any stars at all is, in a sense, a consequence of where we happen to be. We are inside a galaxy. We are embedded in one of those luminous filaments, surrounded by hundreds of billions of other stars, and so the sky above us is populated with light in a way that would not be true for a hypothetical observer positioned in the center of a large cosmic void. Such an observer, if they existed, if life could somehow arise in a region where galaxies are sparse and the nearest star cluster is hundreds of millions of light-years away, would look up at a sky that is almost completely dark. Not the darkness you see between the stars on a clear night, but a darkness so complete that the entire visible universe would appear as a faint smudge on the horizon of their perception, a distant suggestion of structure in an otherwise featureless black. We are fortunate in a purely geometric sense to be where we are, but that fortune is also a kind of illusion. It has allowed us to look at the sky and believe, for most of human history, that the universe is a place of light and presence and structure. It has allowed us to build cosmologies and religions and philosophies around the idea that the cosmos is, at its heart, a place where things exist, where matter is the rule and emptiness is the exception. And that belief, however understandable, however deeply embedded in the experience of being alive on a dense and crowded planet, is not supported by the evidence. The evidence says something different. The evidence says that matter is the exception, that light is the exception, that the rule, the overwhelming, dominant, structurally fundamental rule of the universe, is absence. But it gets worse, because even the matter that does exist, even the stars and galaxies and clusters that make up the luminous web, is not the whole story of what gives the universe its structure. The visible matter, the ordinary atoms that make up everything you have ever touched or seen or measured, accounts for only a small fraction of the total mass energy content of the cosmos, roughly 5%, 5% of everything. The rest is something else entirely, and it does not shine. The first component of that invisible majority is what physicists call dark matter. The name is not metaphorical, it is simply matter, or something that behaves gravitationally like matter, that does not interact with light in any way that allows us to detect it directly. It does not emit light. It does not absorb light. It does not reflect light. It passes through ordinary matter with almost no interaction at all, and yet its gravitational influence is measurable, consistent, and profound. We know it is there not because we can see it, but because of what it does to the things we can see. The rotation of galaxies was one of the first places where the evidence became impossible to ignore. When astronomers measured how fast stars at different distances from the center of a galaxy were orbiting, they expected to find a pattern consistent with the distribution of visible mass, stars and gas and dust. They expected the outer regions of galaxies to orbit more slowly, the way the outer planets of our solar system orbit the sun more slowly than the inner ones, because the gravitational influence of the central mass weakens with distance. Instead, they found that the rotation curves of galaxies were flat. Stars at the outer edges of galaxies were orbiting just as fast as stars closer to the center, sometimes faster. The only explanation consistent with the physics of gravity was that there was far more mass present than the visible matter could account for, mass distributed in a large, roughly spherical halo extending well beyond the visible disk of the galaxy, mass that could not be seen but whose gravitational pull was shaping the motion of everything inside it. This was not a small discrepancy. The amount of invisible mass required to explain the rotation curves of galaxies is roughly 5 to 6 times the amount of visible mass. For every kilogram of ordinary matter in a galaxy, every atom of hydrogen and helium and carbon and iron that makes up the stars and gas and dust, there are roughly 5 or 6 kilograms of something else, something dark, something that participates in gravity but not in light. The visible galaxy is not the galaxy. It is the luminous core of a much larger, much more massive structure that extends into the dark and cannot be directly observed. And this is not unique to individual galaxies. The same invisible mass shows up in galaxy clusters, where the gravitational lensing of background light, the bending of light from distant objects by the gravity of the cluster, reveals far more mass than the visible galaxies and hot gas can account for. It shows up in the large-scale structure of the cosmic web itself, where the filaments and walls that galaxies trace are understood to be the luminous surface of a deeper, darker scaffolding of dark matter halos and filaments that formed first, that shaped the gravitational landscape into which ordinary matter fell, that determined where galaxies would form and how they would cluster. The visible universe is not the structure, it is the decoration on the structure. The galaxies are not the architecture of the cosmos. They are the light caught on an architecture that is mostly invisible. Think about what this means for the picture you have been building. You began with the night sky, which seemed full of stars. Then you learned that the stars are separated by years of empty space. Then you learned that the galaxies are separated by millions of light years, and that the voids between them occupy most of the universe's volume. And now you learn that even the matter that does exist, even the galaxies themselves, are only the visible fraction of a larger, darker, gravitationally dominant structure that cannot be seen at all. The universe is not merely emptier than it looks, it is also more invisible than it looks. The things you can see are not the main things. They are the traces, the residue, the faint luminous outline of something that does not reveal itself to light. And this leads to something more disturbing. Because dark matter, for all its strangeness, at least behaves in a way that is conceptually familiar. It has mass, it gravitates, it clusters, it forms halos and filaments. It is invisible, but it is, in some sense, a thing, a component of the universe that occupies space and exerts force. Whatever it is at the particle level, and that question remains one of the deepest open problems in physics, its gravitational behavior is consistent and measurable. Dark matter is strange, but it is not incomprehensible. It fits within a framework of physics that, while incomplete, is at least coherent. Dark energy is different. Dark energy is not a thing in the same sense. It is not a particle or a field in any way that current physics can fully describe. It is, at its most honest definition, a name given to the unknown cause of an observed effect, the accelerating expansion of the universe. And that effect, and what it implies about the future, is where the story of cosmic emptiness takes a turn that goes beyond the merely vast and into something that feels, the more carefully you examine it, genuinely and profoundly unsettling. To understand dark energy, you first need to understand what the universe is doing. The universe is expanding. This is not a new idea. It has been understood since the early 20th century, when astronomers observed that distant galaxies are moving away from us, and that the farther away a galaxy is, the faster it appears to be receding. This observation, combined with the mathematics of general relativity, led to the understanding that the universe is not a static container in which galaxies move. The universe is a dynamic geometry. Space itself is stretching, and as it stretches, the distances between regions that are not gravitationally bound to each other increase. The galaxies are not flying through space away from a central point of explosion. Space is growing between them, the way dots drawn on the surface of a balloon move apart as the balloon is inflated, not because the dots are moving across the surface, but because the surface itself is expanding. This expansion was expected. What was not expected, what came as a genuine shock to the scientific community when it was first measured in the late 1990s, was that the expansion is accelerating. The universe is not just expanding, it is expanding faster and faster over time. The rate at which space is stretching is increasing, and the cause of that acceleration, whatever is driving the geometry of space-time to expand at an ever-increasing rate, is what we call dark energy. It accounts for roughly 68% of the total energy content of the universe. It is the dominant component of the cosmos, and it is not understood at a fundamental level. Its effect is measurable in the expansion history of the universe, written into the distances and redshifts of billions of galaxies across cosmic time. But what it is, what physical reality underlies the label, remains one of the most profound unanswered questions in all of science. What we do know is what it does, and what it does is separate. It pushes the geometry of space outward, increasing the distances between unbound regions at an accelerating rate. The galaxies that are not gravitationally tied to our own local group, the vast majority of the 2 trillion galaxies in the observable universe, are being carried away from us by this expansion, and they are being carried away faster with every passing moment. Not faster in the sense that they are accelerating through space, but faster in the sense that the space between us and them is growing at an increasing rate, so that the effective recession velocity, the rate at which the distance between us and them increases, grows over time. And here is where the emptiness stops being merely a description of the present and becomes a prediction about the future. Because if the expansion continues to accelerate, and every measurement we have made suggests that it will, then the universe is not simply large and empty now. It is becoming larger and emptier with every moment that passes. The distances are not fixed. They are growing. The isolation is not a static condition. It is a process. And that process has a direction, and that direction is away. The night sky you look at tonight is not the night sky that will exist in the far future. The galaxies you can see, the faint smudges of light that appear in long exposure photographs, the distant islands of stars that populate the observable universe, are visible now because the light they emitted long ago has had time to reach us. But as the universe expands, as the distances grow, as the recession velocities of distant galaxies increase, there will come a point, not in any human timescale, but in the deep future of the cosmos, when the light from those galaxies can no longer reach us, not because the galaxies have gone dark, but because the space between us and them will be expanding faster than light can cross it. They will not disappear. They will simply become unreachable, permanently, irrevocably, not as a matter of technological limitation, but as a matter of geometry. The universe has the capacity to remove things from possibility, not from existence, but from contact, not from reality, but from reach, and it is already doing this. There are galaxies in the observable universe today that are already receding from us faster than light, carried by the expansion of space itself. We can still see them because the light they emitted in the past, when they were closer, is still traveling toward us. But any light they emit today will never reach us. The connection is already severed, even if the image of the connection still lingers in our sky like the light of a star that has already died. This is the shape of the universe's future, not a collapse back into warmth and closeness, not a return to density, but a deepening of the separation that already defines it. A future in which the observable universe, the region from which light can reach any given point, shrinks relative to the total universe, leaving each island of matter more isolated, more alone, more surrounded by an expanding dark that carries everything else beyond the horizon of contact. And this is only the beginning of what the future holds, because the expansion and the isolation are not the only forces at work. There is another process, quieter and more fundamental, that has been operating since the first moments of the universe's existence, and that will continue operating long after the last star has burned out and the last galaxy has faded. It is a process that does not require dark energy or cosmic expansion to do its work. It operates at every scale, in every corner of the cosmos, in every system where energy exists and gradients can form and dissipate. It is the process that physicists call entropy, and it is in its own way as disturbing as anything the universe has yet revealed. But that is a story for what comes next. For now, hold the image that has been building through everything said so far. Hold the picture of a universe that is mostly void, mostly dark, mostly invisible, and mostly expanding away from itself. Hold the picture of a cosmos in which the visible matter, the stars and galaxies and clusters that seem from the ground to fill the sky, is a thin and fragile pattern drawn on top of something much larger, much emptier, and much less interested in the existence of light than the night sky has ever suggested. The universe is not full. It never was, and it is becoming less full with every moment that passes. The darkness is not the background. The darkness is the point. There is a particular quality to the silence of deep space that no recording can capture and no image can convey. It is not the silence of a quiet room, where the absence of sound is defined against the memory of sound. It is the silence of a place where the concept of sound has no meaning, where there is no medium to carry vibration, no air to compress and rarefy, no surface to reflect a wave back to a waiting ear. It is the silence of pure geometry, of distance without content, of space that extends in every direction without offering anything to the senses that evolved to navigate a dense and noisy world. And that silence is not confined to the spaces between stars. It is the dominant condition of the universe. It is what most of the cosmos is, most of the time, in most of the places that exist. When you look at the night sky and feel something, wonder or smallness or the particular vertigo of realizing that the light reaching your eyes has traveled for years or centuries or millennia, you are feeling the right thing. The scale is real. The distance is real. The age of the light is real. But the feeling of fullness, the sense that the sky is populated and present and alive with burning things, that feeling is a product of your position and your biology, not a property of the universe. You are inside a galaxy, surrounded by stars, on a planet dense with matter and warm with energy. You are in one of the most crowded places the universe has to offer. And even here, even in this exceptional location, the nearest star is 4 light-years away, and the nearest galaxy is 5 million light-years distant. Even here, the emptiness is the dominant fact. You are just close enough to the exceptions to mistake them for the rule. The universe does not know you are looking at it. It does not arrange itself to be seen. It does not produce light for the benefit of observers. The stars burn because of physics, because gravity compresses hydrogen until the pressure and temperature are sufficient to fuse atomic nuclei and release energy. They are not fires lit for warmth or navigation or beauty. They are the inevitable consequence of matter falling together under gravity, in a universe that began with a particular distribution of density and energy. They will burn for as long as their fuel lasts, and then they will stop. And the universe will continue, indifferent to their absence, expanding into its own dark future at an accelerating rate, carrying the remnants of those fires farther and farther apart, until the distances between them become so large that even the concept of a shared universe, a cosmos in which different regions can communicate, interact, or know of each other's existence, begins to dissolve. This is not a story about the end of the world. It is not a story about catastrophe or collision or the violent death of stars. It is a story about something quieter, and in its own way, more final. It is a story about the universe becoming what it has always, at its deepest level, already been: mostly nothing, mostly dark, mostly silent, with the brief and temporary exceptions. The stars, the galaxies, the planets, the life, fading slowly into the expanding dark, like embers cooling in a wind that blows from no direction and toward no destination. Entropy is not a word that belongs only to physics textbooks or thermodynamics lectures. It is a word that describes something you already know, something you have felt without having a name for it. You have felt it in the way a fire dies down over hours, the bright flames shrinking to orange coals and then to gray ash, the heat that was concentrated and intense spreading outward into the room and then into the walls, and then into the night air until it is indistinguishable from the background temperature of everything around it. You have felt it in the way a cup of hot coffee cools on a table, the warmth flowing from the liquid into the ceramic into the air, the gradient between the hot thing and the cold room slowly erasing itself until the coffee is the same temperature as its surroundings, and the difference that made it useful, that made it coffee rather than just warm liquid, is gone. You have felt it in the way a sandcastle dissolves in the tide, the careful structure returning to undifferentiated sand, the information encoded in its shape dispersing into the random motion of grains and water. These are not separate phenomena. They are all expressions of the same deep tendency, the same arrow that runs through every physical process in the universe, pointing always in the same direction, from concentrated to dispersed, from ordered to disordered, from structured to uniform, from difference to sameness. The second law of thermodynamics states that in any closed system, entropy, a measure of the number of possible microscopic arrangements consistent with the observed macroscopic state, tends to increase over time. This is not a law in the sense of a rule imposed from outside. It is a statistical inevitability. There are vastly more ways for energy to be spread out than for it to be concentrated. There are vastly more arrangements of matter that look disordered than arrangements that look structured. And so, given time and the freedom to evolve, systems tend toward the more probable states, the spread out, the uniform, the undifferentiated, not because the universe prefers disorder in any meaningful sense, but because disorder is simply more common than order, and physical systems explore their available states with a thoroughness that makes the eventual arrival at high entropy configurations not just likely but, over sufficient time, essentially certain. What this means for the universe is something that takes a moment to fully absorb. The universe began, as best we can determine, in an extraordinarily low entropy state. The Big Bang, or more precisely the earliest moments of the universe's existence that our current physics can describe, was a state of enormous energy density, extreme temperature, and a particular kind of order that, paradoxically, contained within it the seeds of all the structure that would follow. The slight variations in density that existed in those early moments, variations so small they are measured in parts per 100,000, were the gravitational seeds from which everything else grew. Matter fell into those slight overdensities. Gas clouds collapsed. Stars ignited, galaxies formed. The cosmic web took shape. All of this structure, all of this complexity, all of this apparent order, is the universe spending the low entropy inheritance it was born with, converting it into the higher entropy configurations that the second law demands. Stars are, in this sense, entropy engines. They take the low entropy fuel of hydrogen, atoms of the simplest element, packed together under gravity into a dense core, and they convert it into helium and heavier elements, releasing energy in the process. That energy radiates outward into space, spreading from the concentrated point of the star's surface into the vast, cold volume of the surrounding universe, diluting itself across an ever-increasing area, becoming less and less concentrated, less and less useful, less and less capable of doing work. The light that reaches your eyes from a distant star is not the same as the energy that was released in that star's core. It has already been diluted by the square of the distance it has traveled. It has already spread. It is already on its way to becoming indistinguishable from the background radiation that fills the universe, the cosmic microwave background, the faint thermal echo of the Big Bang itself, now cooled to just 2.7 degrees above absolute zero, spread uniformly across the sky in every direction, the most diffuse and uniform and high-entropy radiation field in the observable universe. The cosmic microwave background is, in a sense, a picture of entropy in action. It is the remnant of a time when the universe was hot and dense and filled with a plasma of charged particles that scattered light in every direction. As the universe expanded and cooled, that plasma recombined into neutral atoms, and the light that had been trapped in the plasma was suddenly free to travel. It has been traveling ever since for roughly 13.8 billion years, spreading and cooling and diluting as the universe expanded around it. What was once a brilliant, hot, dense radiation field is now a faint microwave glow, barely above absolute zero, nearly perfectly uniform in every direction. It is the universe's past, written in the language of entropy, and it tells a story of irreversible change, of energy that was once concentrated and is now spread so thin that it barely registers against the cold geometry of expanding space. But the entropy story of the universe is not finished. It is, in fact, barely begun. The universe is approximately 13.8 billion years old. The stars that exist today, including our own sun, are burning in what cosmologists sometimes call the stelliferous era, the age of stars, the period in cosmic history when the universe is bright enough and dense enough and energetic enough to sustain the nuclear fires that make galaxies shine. This era will not last forever. It cannot last forever because the fuel is finite, and the second law is not. The hydrogen that stars burn is being consumed, converted into helium and heavier elements, and while new stars continue to form from the gas and dust that remains in galaxies, the rate of star formation has already been declining for billions of years. The universe made most of its stars long ago, in a period of intense activity roughly 10 billion years in the past, and since then the rate has been falling. The universe is not in the middle of its stellar life. It is past the peak. The fires are, on a cosmic scale, already beginning to dim. This is not a dramatic statement. It is a quiet one. The dimming is slow by any human measure. It will take billions of years for the effects to become significant, even on galactic scales. But the direction is clear and the direction does not reverse. The universe is not cycling. It is not breathing in and out, contracting and expanding, brightening and dimming in a rhythm that will eventually return it to something like its current state. It is moving in one direction, along the arrow of entropy, from the low entropy past toward the high entropy future, and that future is not a return to brightness. It is a continuation of the dimming that has already begun. Consider what the galaxy will look like in 5 billion years, when our own sun has exhausted its hydrogen fuel and expanded into a red giant, eventually shedding its outer layers and leaving behind a dense, cooling remnant called a white dwarf. The sun will not explode. It will not go dark suddenly. It will simply stop being a main sequence star, stop being the kind of star that burns steadily and brightly for billions of years, and become something smaller, denser, and gradually cooling. A white dwarf is not a dead star in the sense of being inert. It is a hot, dense object that radiates the thermal energy stored in its interior, slowly cooling over billions of years. But it produces no new energy. It is spending a fixed reserve, and that reserve will eventually run out. Given enough time, far more time than the current age of the universe, a white dwarf will cool to the temperature of its surroundings and become what physicists call a black dwarf, a cold, dark, inert mass of crystallized matter, invisible against the background of space, contributing nothing to the light of the galaxy. The Milky Way will be full of white dwarfs long before it runs out of gas for new star formation. And eventually it will be full of black dwarfs, cold remnants of stars that burned for billions of years and then went dark, one by one, as their thermal reserves were exhausted. The galaxy will not disappear, the matter will still be there, but the light will be gone. The fires will have burned out not in a catastrophe, not in a single dramatic event, but in the slow, patient, inevitable way that entropy claims everything it is owed. But it gets worse. Because the fate of stars is not the only process at work in the long-term future of the universe. There is another actor in this story, one that operates on timescales so vast that they make the lifetime of a star seem like a brief flash of light in a dark room. That actor is the black hole, and its role in the ultimate fate of the cosmos is both central and deeply strange. Black holes form when massive stars exhaust their nuclear fuel, and their cores collapse under gravity, compressing matter to such extreme densities that the escape velocity from the resulting object exceeds the speed of light. Nothing that falls within the boundary of a black hole, the event horizon, can escape. Not matter, not radiation, not information in any form that can be extracted by an outside observer. Black holes are, in the most literal physical sense, regions of spacetime from which the universe has been permanently removed from contact. They are the ultimate expression of the isolation that runs through the entire story of the cosmos. Regions where the separation between inside and outside is not a matter of distance but of geometry, enforced by the curvature of spacetime itself. In the far future of the universe, after the stars have burned out and the galaxies have aged and the rate of new star formation has fallen to nearly zero, black holes will be among the dominant structures in the cosmos. The supermassive black holes that sit at the centers of galaxies, objects with masses millions or billions of times that of the Sun, will persist long after the stars around them have faded. Stellar mass black holes, the remnants of massive stars that collapsed at the ends of their lives, will drift through the dark remnants of galaxies, occasionally merging with each other or with the supermassive black holes at galactic centers, growing slowly larger as they absorb whatever matter comes within their gravitational reach. For an almost incomprehensible span of time, the universe will be a place of black holes and cooling remnants and the faint, diluted radiation of the cosmic background, still expanding, still cooling, still moving along the arrow of entropy toward the uniform, featureless maximum entropy state that the second law points toward. The timescales involved are not merely large. They are large in a way that requires a different kind of number than the ones used to describe the age of the universe or the lifetime of a star. The current age of the universe is approximately 13.8 billion years, a number written as 1.38 times 10 to the 10th power. The lifetime of the longest-lived stars, the small, cool red dwarf stars that burn their hydrogen so slowly and so efficiently that they can shine for trillions of years, is measured in numbers like 10 to the 13th or 10 to the 14th power. The timescale on which black holes dominate the universe before other processes begin to change them is measured in numbers like 10 to the 40th power. And the timescale on which even black holes may eventually change is measured in numbers that make 10 to the 40th look small. This is where the physics becomes genuinely strange, and where the story of the universe's future takes a turn that even the most careful scientific imagination struggles to fully picture. In 1974, the physicist Stephen Hawking demonstrated theoretically that black holes are not perfectly black. They emit a faint thermal radiation, now called Hawking radiation, as a consequence of quantum mechanical effects near the event horizon. The details of the mechanism involve the behavior of quantum fields in curved spacetime, and the mathematics is subtle, but the result is clear. Black holes slowly lose mass by radiating energy, and given sufficient time, they will evaporate completely. The rate of evaporation is extraordinarily slow for large black holes. A stellar mass black hole would take roughly 10 to the 67th years to evaporate, and a supermassive black hole would take far longer. But the direction is one way. Black holes are not permanent. They are, like everything else in the universe, temporary structures spending a finite reserve of energy in a universe that tends toward uniformity. When the last black hole has evaporated, when the last concentrated mass energy in the universe has been converted into the diffuse thermal radiation of Hawking evaporation and spread into the expanding void, what remains? The answer, according to the leading models of the universe's long-term future, is something that is almost impossible to describe in terms that carry any emotional weight, because it is a state so close to nothing that the distinction between it and nothing becomes almost philosophical. What remains is a universe of extreme dilution, photons and other particles spread across a volume so vast that the average distance between any two particles is measured in numbers that have no analogy in human experience, all of it expanding, all of it cooling, all of it moving toward the thermal equilibrium that the second law has been pointing toward since the first moment of the universe's existence. This state, sometimes called the heat death of the universe, though the name is misleading because it implies warmth, and what it actually describes is the opposite, is not a violent end. It is not a collapse, or an explosion, or a dramatic transformation. It is the universe arriving after an almost infinite journey at the state of maximum entropy, a state where no gradients remain, where no energy flows from one place to another, where no work can be done, where no events of any significance can occur, because events require differences in temperature and density and energy, and all differences have been erased. It is the universe becoming, in the most complete sense possible, uniform, featureless, still. The heat death is not a certainty. It is the leading scenario based on current understanding, on the measured acceleration of cosmic expansion, on the second law of thermodynamics, on the theoretical prediction of Hawking radiation, on the absence of any known mechanism that would reverse the arrow of entropy on cosmological scales. But physics is not finished, and the universe may contain surprises that current models do not anticipate. There may be processes operating on timescales or at energy scales that are beyond the reach of current observation or theory. The honest position is that the heat death is the best supported prediction of the universe's ultimate fate, not a guaranteed outcome. But the honest position also acknowledges that every piece of evidence gathered so far points in the same direction, and the direction does not lead toward renewal or return. It leads toward the dark. What is perhaps most disturbing about the heat death scenario is not the end state itself, the featureless, uniform, eventless cosmos, but the process of getting there, because the process is not a sudden transition. It is a gradual fading, a slow dimming of the universe's capacity for complexity and structure and event, stretched across timescales so vast that the entire history of the universe from the Big Bang to the present day is a negligible fraction of the journey. The universe will spend most of its existence in a state of increasing emptiness, increasing darkness, increasing silence. The bright era, the era of stars and galaxies and planets and life, is not the universe's normal condition. It is an early and temporary phase, a brief period of concentrated energy and rapid change in a history that is mostly characterized by the slow, patient, irreversible spread of that energy into the void. We exist in the bright era. We exist in the exceptional moment, the cosmically brief window when the universe is energetic enough and structured enough to support the kind of complexity that produces stars and planets and chemistry and biology and minds capable of looking up at the night sky and asking what it all means. And that window is not permanent. It is not the universe's destination. It is a phase, like the brief flare of a match before the wood catches and the flame settles into something slower and dimmer and eventually dark. But it goes deeper, because the fading of the universe is not only a physical process, it is also, in a sense, that becomes more unsettling the longer you sit with it, an informational process. The universe does not only lose energy as it ages, it loses structure, it loses contrast. It loses the differences in gradients and organized patterns that carry information, that make one region distinguishable from another, that make one moment different from the next, that make the universe a place where things happen rather than a place where things simply are. And as those differences fade, as the universe approaches the uniform, featureless state of maximum entropy, the capacity for anything to be recorded or remembered or known diminishes with them. Consider what it means for information to exist in a physical system. Information, in the technical sense used by physicists and information theorists, is a measure of the distinguishability of states, the degree to which one configuration of a system can be told apart from another. A book contains information because the arrangement of ink on its pages is one of an astronomically large number of possible arrangements, and the specific arrangement encodes something that can be read and interpreted. A star contains information in its structure, in the distribution of its mass, the composition of its layers, the pattern of its magnetic field, the history of its nuclear burning written in the ratios of its elemental abundances. A galaxy contains information in the positions and velocities and ages of its stars, in the distribution of its gas and dust, in the record of its mergers and interactions with other galaxies. The universe, at any given moment, is an enormous information-bearing structure, and the complexity of that structure, the richness of its distinguishable states, is a measure of how far it is from the featureless uniformity of maximum entropy. As entropy increases, that information does not disappear in a strict physical sense. The laws of physics are, at the fundamental level, time reversible, and information is conserved in the evolution of quantum states, but it becomes inaccessible. It becomes encoded in correlations between particles so diffuse and so complex that no physical process could ever extract or use it. It becomes, for all practical purposes, lost. Not erased, but buried so deeply in the noise of a high-entropy universe that it might as well not exist. The history of the universe, the record of every star that burned, every galaxy that formed, every planet that cooled, every organism that lived and died, will be encoded in the quantum state of a universe of diffuse radiation and cold remnants, in principle recoverable, but in practice as inaccessible as a message written in smoke, dispersed by a hurricane. The universe will remember nothing, not because memory is impossible, but because the physical substrate that memory requires, the differences, the gradients, the structures, will have been erased by the patient work of entropy. This is not a metaphor. It is a physical prediction. The universe is moving toward a state in which the concept of a record, of a past that can be read from the present, becomes meaningless. Not because the past did not happen, but because the physical traces of the past will have been so thoroughly dispersed and diluted that no observer, no instrument, no process could reconstruct them. The universe will become, in the deepest sense, amnesiac. It will carry within it the quantum echoes of everything that ever happened, but those echoes will be indistinguishable from noise, and noise is, by definition, the absence of meaning. And this connects back to the expansion, to the dark energy, to the accelerating separation of the universe's regions, because the expansion does not only increase the physical distances between galaxies, it also dilutes the radiation that fills the universe, stretching the wavelengths of photons and reducing their energy, spreading the information they carry across ever larger volumes of space. The cosmic microwave background, already the most dilute and uniform radiation field in the observable universe, will continue to cool and dilute as the universe expands. The photons from distant galaxies, already redshifted by the expansion, will be redshifted further, their energies reduced, their wavelengths stretched toward the infrared and then the microwave, and then the radio, and then wavelengths so long that they carry almost no energy at all. The universe will not go dark all at once. It will fade, frequency by frequency, wavelength by wavelength, as the expansion stretches the light out of existence. There is a particular image that captures something of this process, though no image can fully convey it. Imagine a message written on the surface of a balloon. As the balloon is inflated, the letters stretch. At first they are still readable, still recognizable as letters, still carrying the information of the original message. But as the balloon continues to expand, the letters grow larger and thinner, the ink spreading across a greater area, the contrast between the ink and the surface diminishing as the ink thins. Eventually, the letters are so large and so thin that they are indistinguishable from the background. The message is still there. In principle, the ink has not been removed, the surface has not been erased, but it cannot be read. It has been expanded into illegibility. This is what the universe is doing to its own light, to its own information, to the record of its own history. It is inflating itself toward illegibility, but it gets worse, because the expansion does not only affect the light that already exists, it affects the possibility of future communication, future connection, future knowledge. As the universe expands, and the distances between unbound regions grow, the number of regions that can send signals to any given point decreases. The observable universe, the region from which light has had time to reach us since the Big Bang, is not the same as the total universe. It is a sphere defined by the distance light can travel in the age of the universe, and it is surrounded by regions that are, in principle, part of the same universe but from which no signal has yet arrived. As the universe ages and expands, the observable universe of any given point does not simply grow to encompass more of the total universe. In an accelerating expansion, the observable universe of a future observer may actually be smaller than ours, not because the universe has contracted, but because the accelerating expansion is carrying distant regions beyond the horizon, faster than the passage of time can bring their light to us. A future observer, living in a galaxy billions of years from now, will look out at a sky that contains fewer galaxies than ours does today. Not because galaxies have been destroyed, but because the expansion will have carried them beyond the horizon of observability. The local group, the cluster of galaxies that includes the Milky Way and Andromeda, and a few dozen smaller companions, will remain gravitationally bound, its members held together against the expansion by their mutual gravity. But everything beyond the local group will eventually recede beyond the cosmological horizon, their light redshifted to invisibility, their existence undetectable by any instrument. A future observer in the local group will see, beyond their own cluster of galaxies, not a universe full of distant lights, but a darkness that extends in every direction without limit, offering no evidence that anything else exists. This is not a distant or hypothetical scenario in the sense of being speculative. It is the straightforward prediction of the standard cosmological model based on the measured value of the cosmological constant, the parameter that quantifies the effect of dark energy on the expansion of the universe. If that value remains constant, as current observations suggest it does, then the recession of distant galaxies beyond the observable horizon is not a possibility. It is a certainty. It is already happening. The galaxies that are currently at the edge of our observable universe are already moving away from us at rates that will eventually carry them beyond the reach of any future signal we could send. The universe is already in the process of erasing its own breadth from the perspective of any local observer. Think about what this means for the concept of cosmology itself, for the project of understanding the universe by observing it. The cosmology we practice today is possible because we can see across billions of light years, because the universe is old enough and transparent enough that the light from distant galaxies has had time to reach us, because the expansion has not yet carried those galaxies beyond our horizon. We can measure the cosmic microwave background and read the conditions of the early universe. We can observe the distribution of galaxies and reconstruct the history of cosmic structure formation. We can measure the redshifts of distant supernovae and determine the expansion history of the universe. We can, in short, do cosmology. We can study the universe as a whole because we have access to a vast and information-rich sky. But a future observer, living in the local group after the rest of the universe has receded beyond the horizon, will not have this access. They will see their own cluster of galaxies, merged by then into a single large elliptical galaxy, surrounded by darkness. They will have no evidence of the cosmic microwave background, which will have been redshifted to wavelengths so long and energies so low that it will be undetectable against the noise of their instruments. They will have no evidence of the large-scale structure of the universe, the filaments and voids and superclusters, because all of that structure will be beyond their horizon. They will have no way to measure the expansion of the universe because there will be no distant galaxies whose redshifts they can measure. They will be, in every observational sense, alone in a universe that appears to consist of a single galaxy, surrounded by infinite dark. If those future observers are scientists, if intelligence persists in the universe long enough to encounter this situation, they will face a profound epistemological problem. The evidence that would allow them to reconstruct the history and structure of the universe will be gone. Not hidden, not difficult to access, but genuinely absent from their observable universe. They will not be able to discover that the universe began in a hot, dense state. They will not be able to measure the cosmic microwave background. They will not be able to determine that their galaxy is one of trillions. They will not be able to infer the existence of dark energy or the history of cosmic expansion. The universe will have, through its own expansion, erased the evidence of its own past from their sky. They will be scientists in a universe that has hidden its own history from them, and they will have no way of knowing what they cannot see. This is one of the most quietly devastating implications of the accelerating expansion. It means that the universe we can observe today, the rich, information-dense, cosmologically legible universe that has allowed us to construct the standard model of cosmology, is a temporary gift of our position in cosmic time. We exist early enough in the universe's history that the evidence is still present, still accessible, still readable. The light from the early universe has had time to reach us. The distant galaxies have not yet receded beyond our horizon. The cosmic microwave background is still detectable. We are, in a sense, living in the golden age of cosmology, not because our instruments are the best they will ever be, but because the universe itself is still showing us its full extent. That window is closing, slowly, imperceptibly on any human timescale, but closing nonetheless. The universe is in the process of becoming less knowable, and it will continue that process until the knowable universe is a single island of matter in an infinite and featureless dark, and even that island will not last. Even the local group, held together by gravity against the expansion, will not be permanent. The galaxies within it will continue to interact, to merge, to redistribute their stars through gravitational encounters. The Milky Way and Andromeda are already on a collision course, expected to begin their merger in roughly 4 billion years. The result will not be a catastrophic destruction of stars. The distances between individual stars are so large that direct collisions will be rare, but a gravitational reshuffling, a slow and violent rearrangement of the two galaxies' structures into a new, larger, elliptical galaxy. The gas that fuels star formation will be disrupted and consumed in a burst of new stellar birth, and then the merged galaxy will settle into a quieter state, its star-forming gas largely exhausted, its stellar population aging and cooling. This is the future of our galaxy, not destruction, but transformation into something older and quieter. A large elliptical galaxy, its blue star-forming regions replaced by the red and orange light of aging stars, its gas consumed, its structure settled into the smooth, featureless distribution of an old stellar population, and then, over billions of years, the aging and the cooling and the dimming, as the stars burn out one by one and the galaxy becomes, star by star, a little darker, a little colder, a little more like the silence that surrounds it. The universe is not ending. That is perhaps the most unsettling thing about all of this. It is not collapsing, not exploding, not being destroyed. It is simply continuing, expanding, cooling, dimming, aging, in the direction that physics has always pointed it. The stars are burning, the galaxies are separating, the entropy is increasing, the expansion is accelerating, and all of these processes are not catastrophes. They are the normal operation of a universe that was never designed for permanence, never arranged for the convenience of observers, never structured around the assumption that the bright and complex and warm things would last. They are the universe doing what the universe does, which is to say, moving from the low entropy past toward the high entropy future, spending its inheritance of order and structure and concentrated energy in the patient, irreversible way that the second law demands. And somewhere in the middle of that process, somewhere in the brief, bright, energetic phase between the hot beginning and the cold end, a planet formed around an ordinary star, in an ordinary galaxy, in an ordinary region of the cosmic web, and on that planet, matter organized itself into structures of sufficient complexity to look up at the sky and ask what it was seeing. And what it was seeing, though it took a long time to understand this, was not a universe built for looking. It was a universe in the process of becoming something that cannot be looked at, because there will be nothing left to see. There is a question that sits underneath all of this, one that the science does not answer and perhaps cannot answer, but that the science makes impossible to avoid. It is not a question about physics or cosmology or the mathematics of expansion. It is a question about what it means to be the kind of thing that asks questions, to be a mind, an observer, a point of awareness embedded in a universe that is, by every measure we have, overwhelmingly indifferent to the existence of minds. The question is not why the universe is the way it is. The question is what it means that we are here to notice, not in a comforting sense, not in the sense that our noticing gives the universe meaning, or that consciousness is the universe becoming aware of itself, or any of the other formulations that have been offered over the years to soften the blow of cosmic scale. Those formulations are understandable. They are the mind's attempt to find a foothold in a landscape that offers none, but they do not change the physics. They do not alter the expansion rate or slow the increase of entropy, or bring the distant galaxies back within reach. They are responses to the universe, not descriptions of it. And the universe, described accurately, does not support them. What the universe supports when described accurately is this: matter is rare, complex matter is rarer, self-replicating chemistry is rarer still, and minds, systems capable of modeling their environment, of representing the past and anticipating the future, of asking what the universe is and what they are inside it, are so rare that we have not yet found evidence of a single other example beyond the ones walking around on this planet. We are, as far as we can determine, alone in the observable universe, not because the universe is hostile to life in the way that a predator is hostile to prey, but because the conditions required for life are so specific, so dependent on the right chemistry and the right energy gradients and the right planetary environment, that they appear to be met only in the narrowest of circumstances, in the thinnest margins of the cosmic web, for the briefest of windows in the universe's long history. The Fermi paradox, The observation that a universe as large and as old as ours should, if life arises readily, be full of evidence of intelligent civilizations, and yet we see none, is not resolved by the science of cosmic emptiness, but it is contextualized by it. A universe that is mostly void, mostly dark, mostly composed of regions where galaxies are sparse and stars are separated by years of empty space, is a universe in which the emergence of life is not a common event, but an exceptional one. The cosmic web is not a network of inhabited worlds connected by the threads of civilization. It is a structure of gas and dark matter and gravity, and the inhabited worlds, if they exist beyond our own, are separated from each other by distances so large that communication between them, even at the speed of light, would take thousands or millions of years. The universe is not a community. It is an archipelago of isolated points, each one separated from the others by a sea of nothing so vast that the concept of connection barely applies. And even within those isolated points, even on the rare planets where chemistry has organized itself into something that breathes and thinks and wonders, the window of habitability is not permanent. Stars age, planets cool or overheat. The conditions that allow complex chemistry to persist are maintained by a balance of energy inputs and outputs that is, on cosmic timescales, temporary. The Sun will remain stable for roughly another 5 billion years, after which its evolution into a red giant will make the inner solar system uninhabitable. 5 billion years is an enormous span of time by human standards, but it is a finite one, and it is small compared to the timescales on which the universe will continue to exist after the last star has burned out. Life, wherever it exists in a window, and windows close, but it goes deeper. Because the rarity of life is not only a spatial fact, not only a matter of life being confined to rare planets and rare solar systems in ordinary galaxies, it is also a temporal fact. The universe has not always been capable of supporting life as we understand it, and it will not always be capable of supporting it in the future. In the early universe, in the first hundreds of millions of years after the Big Bang, the cosmos was too hot, too dense, and too chemically simple for the kind of chemistry that life requires. The first stars were made almost entirely of hydrogen and helium, the elements produced in the Big Bang, and they burned hot and fast and died in supernovae that seeded the surrounding gas with the heavier elements that chemistry needs. Carbon, oxygen, nitrogen, iron, phosphorus, the elements that make up living things, were not present in significant quantities in the early universe. They had to be made, forged in the cores of stars, and scattered by their deaths. Over billions of years of stellar evolution, the universe had to age before it could support life. It had to go through generations of stars, each one living and dying and enriching the interstellar medium with the products of its nuclear burning, before the raw materials for biology were available in sufficient quantities. The solar system formed roughly 4.6 billion years ago, roughly 9 billion years after the Big Bang, in a galaxy that had already been through multiple generations of stellar birth and death. The heavy elements in your body, the carbon in your cells, the oxygen in your lungs, the iron in your blood, were made in stars that lived and died before the sun was born. You are, in a very literal sense, the product of a long chain of stellar deaths, each one necessary to produce the chemistry that eventually, after billions of years of planetary evolution, gave rise to the kind of complexity that can ask where it came from. This is often presented as a beautiful fact, and in a certain light it is, but it is also a fact about constraint. Life did not arise early in the universe's history because the universe was not ready for it. Life arose in a specific window, after enough stellar generations had passed to enrich the interstellar medium with heavy elements, but before the universe had aged so far that star formation had declined to the point where the energy gradients necessary for life were no longer available. We exist in that window. We exist in the cosmically brief period when the universe is old enough to have the right chemistry and young enough to still have the right energy. And that window, like all windows in a universe governed by entropy and expansion, is temporary. In the far future, as star formation declines and the existing stars age and cool, the energy gradients that drive chemistry and biology will become harder to find. The universe will not become hostile to life in the way that a desert is hostile to a fish. It will not actively destroy the conditions for life. It will simply stop providing them. The fires that warm the planets will go out, one by one, as the stars that host them exhaust their fuel. The chemistry that drives metabolism will slow and stop as the energy inputs that power it fade. Life, wherever it exists, will find itself in a universe that is gradually withdrawing the conditions that made it possible, not through any act of destruction, but through the simple, patient operation of entropy and the arrow of time. There is something in this that resists easy description. It is not tragedy in the human sense, because tragedy requires an audience and a narrative and a sense that things could have gone differently. The universe does not offer those things. It does not have an audience beyond the minds it briefly produces, and it does not have a narrative in the sense of a story with a purpose or a direction beyond the one imposed by physics. The fading of the conditions for life is not a tragedy. It is a physical process. But it is a physical process that, when understood fully, produces in the minds that understand it something that feels very much like the recognition of tragedy. The recognition that the thing you are, the thing that is capable of understanding this, is itself a temporary exception in a universe that does not make exceptions permanent. And this leads to something more disturbing. Because the temporariness of life is not the most unsettling thing about the universe's relationship to complexity and structure. The most unsettling thing is the proportion. The universe will exist, according to the best current models, for a time so vast that the entire period during which stars shine and planets orbit and life is possible is a negligible fraction of the total. The stelliferous era, the age of stars, will last perhaps 100 trillion years, from the Big Bang to the death of the last red dwarf. That sounds enormous. But the timescales that follow, the era of black hole dominance, the era of Hawking evaporation, the approach to heat death, are measured in numbers that make 100 trillion years look like the first second of a very long day. The bright era, the era of life, is not the universe's main event. It is the opening act of a performance that will continue in darkness and silence for an almost incomprehensible duration after the curtain has fallen on everything that shines. The universe will spend the overwhelming majority of its existence in a state that cannot support life, cannot support complexity, cannot support the kind of organized, energy-driven chemistry that produces minds. The brief window of stellar warmth and chemical richness that we inhabit is not the universe's purpose. It is a phase transition, a temporary state between the hot, dense beginning and the cold, diffuse end, and it is characterized by the kind of complexity and structure that the universe will never again produce once it has passed. We are not living in the universe's prime. We are living in its youth, in the brief, bright, energetic period before the long, dark, cold adulthood that will constitute most of its history. This reframing from the universe as a place of light and life to the universe as a place that briefly and temporarily produces light and life before settling into a far longer state of darkness and silence is not a pessimistic interpretation of the science. It is the science. The numbers support it, the physics supports it, the expansion history, the entropy calculations, the stellar evolution models, the predictions of Hawking radiation and black hole evaporation, all of them point in the same direction. The universe is not a place built for life. It is a place that, under specific conditions that exist for a limited time in a limited region of its total volume, happens to produce life, and the conditions are already changing. The universe is already moving past the peak of its star-forming activity, already in the declining phase of the stelliferous era, already on the long slope toward the darkness that will define most of its future. But it gets worse, because even the structure of the universe that we can observe, even the cosmic web, the filaments and walls and clusters that represent the organized, gravity-shaped architecture of the visible cosmos, is itself a temporary state. The large-scale structure of the universe formed over billions of years as dark matter halos grew and merged, as gas fell into gravitational wells and cooled and formed stars, as galaxies assembled and clustered along the filaments of the cosmic web. It is a structure that took most of the universe's current age to build, and it is a structure that the expansion is already beginning to dismantle, not by destroying the gravitationally bound systems, but by separating them from each other, by carrying the unbound regions beyond the horizon, by turning the interconnected web of the observable universe into a collection of isolated islands, each one surrounded by an expanding dark that grows wider with every passing moment. The cosmic web, seen in its full extent today, is a snapshot of a structure in transition. The filaments that connect galaxy clusters across hundreds of millions of light years are not permanent features of the universe. They are the current state of a system that is being pulled in two directions simultaneously. Gravity pulling matter together along the filaments, dark energy pulling the geometry of space apart. On the scales of individual galaxy clusters and groups, gravity wins. The bound systems remain bound, their members held together against the expansion. But on the larger scales, on the scales of the filaments themselves and the superclusters they connect. The expansion is winning. The connections are stretching. The filaments are thinning. The web is, on the largest scales, already beginning to dissolve into the isolation that the future will complete. There is a particular kind of loneliness in this picture that is different from any human experience of loneliness. Human loneliness is the absence of connection in a world where connection is possible. The feeling of being separated from others who exist and could, in principle, be reached. The loneliness of the cosmic future is different. It is the loneliness of a universe in which connection becomes geometrically impossible, in which the expansion of space places other regions permanently beyond reach, not because they are unwilling to connect, not because the distance is merely large, but because the geometry of spacetime itself enforces the separation. It is loneliness as a physical law, isolation as a feature of the universe's structure, built into the expansion rate and the value of the cosmological constant, as fundamental and as inescapable as gravity. And this isolation is not something that will happen in the future. It is something that is happening now, and has been happening since the moment the universe began to expand. Every galaxy, beyond the local group, is already moving away from us. Every photon emitted by those galaxies is already being redshifted by the expansion, its energy reduced, its wavelength stretched. The connection between us and the rest of the universe is not a stable thing that will one day be severed. It is a thing that has been fraying since the beginning, that is fraying now, that will continue to fray until the last thread of light from the last visible galaxy has been stretched beyond detection and the sky goes dark beyond the boundaries of our own gravitationally bound island. What does it mean to exist in a universe that is, at its largest scales, in the process of separating itself into unreachable fragments? What does it mean to be a mind in a cosmos that is actively reducing the amount of the cosmos that any mind can know? These are not questions with answers in the scientific literature. They are questions that the science raises and then leaves open, because science describes what is and what will be, but it does not tell you what to feel about it. The feeling is yours to have, and it is not a comfortable one. There is a concept in cosmology called the particle horizon, the boundary beyond which no particle or signal has had time to reach us since the Big Bang. Everything within the particle horizon is, in principle, part of our observable universe. Everything beyond it is not inaccessible because of distance alone, but because the universe has not been old enough for light from those regions to reach us. As the universe ages, the particle horizon expands, and more of the universe becomes observable. But in an accelerating expansion, there is also an event horizon, a boundary beyond which events happening now will never be able to send signals that reach us, because the expansion will carry those regions away faster than the signals can travel. The event horizon does not expand with time. In an accelerating universe, it shrinks. The region of the universe from which we can ever receive future signals is not growing. It is contracting. The universe is not opening up to us as it ages. It is closing down. This is a precise and measurable prediction of the standard cosmological model, and it is one of the most quietly disturbing facts in all of modern science. The universe is not becoming more knowable as it ages. It is becoming less knowable. The information available to any local observer is not increasing with time. It is decreasing. The cosmos is, in a very literal sense, hiding itself from its own observers, not through any act of concealment, but through the simple operation of its own geometry. The expansion carries information beyond the horizon. The entropy dilutes the signals that remain. The stars burn out and the light fades, and the universe becomes, piece by piece, region by region, galaxy by galaxy, a place that cannot be known because it cannot be seen. Consider the implications for any civilization that might exist in the far future of the universe, not in the immediate future, not in the next billion or 10 billion years, when the universe will still be recognizable as the one we inhabit today, but in the deep future, after the expansion has carried the distant galaxies beyond the horizon, after the last stars have burned out, after the universe has settled into the long, dark era of cooling remnants and evaporating black holes. Any minds that exist in that era, and the question of whether minds can exist in such an era is itself deeply uncertain, will inhabit a universe that is almost unrecognizably different from the one we know. They will have no stars to navigate by, no galaxies to observe, no cosmic microwave background to measure, no evidence of the large-scale structure that defined the universe's history. They will be in every observational sense alone in a dark and nearly featureless cosmos, with no way to reconstruct the history that led to their existence, and no way to know that the universe was ever anything other than what they see around them. If those future minds are curious, If they ask the same questions we ask, if they look out at their universe and try to understand it, they will be doing science in a universe that has hidden its own past from them. They will construct models of a cosmos that appears to consist of a single island of matter in an infinite dark, and those models will be, from their perspective, complete and consistent because they will have no evidence of anything beyond their horizon. They will not know what they are missing. They will not know that the universe was once full of galaxies, that the sky was once populated with light, that the cosmic web once stretched across billions of light years in every direction. That knowledge will have been carried beyond their horizon by the expansion, erased from their observable universe as thoroughly as if it had never existed. And here is the thought that sits at the edge of this realization, the one that is hardest to hold without feeling something shift in your understanding of your own position. We are not those future observers. We exist now, in the bright era, with access to a universe that is still showing us its full extent. We can see the cosmic microwave background. We can observe the large-scale structure. We can measure the expansion history. We can, in principle, know the universe in a way that no observer in the far future will be able to. We are, in a sense, the most cosmologically privileged observers that will ever exist, not because we are special, not because the universe arranged itself for our benefit, but because we happen to exist at a time when the evidence is still present, when the light has not yet faded, when the horizon has not yet closed. But that privilege is not a comfort, it is a responsibility and a vertigo, because what we can see, when we look carefully enough, is not a universe that rewards the looking. It is a universe that reveals, the more carefully it is examined, how little of it is accessible, how much of it is dark, how temporary the conditions that allow us to see it are, and how completely the future will erase the evidence of everything we are learning now. We are reading a book that is being burned as we read it, and the burning is not a catastrophe. It is the normal operation of a universe that was never a library. It was always a fire. The cosmic web, the dark matter scaffolding, the accelerating expansion, the entropy, the fading stars, the closing horizons, these are not separate problems or separate mysteries. They are facets of a single, coherent picture of a universe that is structured around absence, driven by processes that increase separation and decrease contrast, and moving toward a future that is defined not by what it contains, but by what it has lost. The picture is not incomplete. It is, in its broad outlines, one of the most well-supported and carefully tested pictures in the history of science, and what it shows is not what the night sky suggests. It shows a universe that is mostly nothing, mostly dark, mostly expanding away from itself, and mostly indifferent to the brief and fragile exceptions that have arisen within it. The exceptions are real. The stars are real. The galaxies are real. The planets are real. The chemistry is real. The life is real. The minds are real. But they are exceptions, and the universe does not make exceptions permanent. It makes them temporary, and it makes the temporary things feel, from the inside, like the whole story, because the inside of a temporary thing is all that a temporary thing can know. You are inside the exception. You are inside the brief, bright, energetic phase of a universe that will spend most of its existence in a state that cannot produce you, and the universe does not know this about you. It does not know you are here. It does not know you are looking. The darkness between the stars is not waiting for you to fill it. The voids between the galaxies are not empty in anticipation of something that will come to occupy them. The expansion is not carrying the galaxies away to make room for something else. The entropy is not increasing toward a purpose. These processes have no direction in the sense of intention. They have direction only in the sense of physics, the direction imposed by the second law, by the geometry of spacetime, by the value of the cosmological constant, by the initial conditions of the Big Bang. They are not going anywhere. They are simply doing what they do, which is to say, they are making the universe more like itself, more like what it has always, at its deepest level, been: vast, dark, cold, expanding, indifferent. And somewhere in the middle of all of that, somewhere in the thin, luminous, temporary margin between the hot beginning and the cold end, you are here, looking up, asking what it means. And the universe, in its vast and patient silence, does not answer. Not because the answer is hidden, but because the universe was never the kind of thing that answers. There is a specific kind of silence that belongs to the very large. Not the silence of a quiet room, not the silence of a forest at night, not even the silence of a desert under a moonless sky. Those silences are defined by the absence of familiar sounds, the hush that falls when the usual noise stops. The silence of the very large is different in kind, not just in degree. It is the silence of a scale at which the concept of sound has no purchase. at which the vibrations that carry meaning through air and water and solid matter are so diluted by distance that they cease to exist as anything other than the faintest statistical whisper in the thermal noise of the universe. It is the silence of a place where the question of whether anyone is listening has no answer, because the question itself assumes a proximity that does not exist. When astronomers study the large-scale structure of the universe, when they map the positions of millions of galaxies across billions of light years and construct the three-dimensional picture of the cosmic web, what they are doing is, in a sense, making the silence visible. The maps they produce show the filaments and walls and clusters as bright threads and nodes against a dark background, and the dark background is the voids. But the maps are deceptive in the same way that all representations of the universe are deceptive. They compress the scale, they flatten the distances, they make the structure look denser and more connected than it is. In reality, the bright threads are separated by distances so large that the thread itself, the filament of galaxies that looks, on the map, like a continuous structure, is mostly empty space. The galaxies along a filament are not touching. They are not even close by any standard that the word close implies. They are separated by millions of light years, connected only by the invisible gravitational influence of the dark matter halos that surround them. And the filament itself is a structure defined more by what it is not a void, not a wall, not a cluster, than by any positive density of matter. The cosmic web is, in this sense, a structure of gradations rather than boundaries. The voids are not sharply edged chambers with walls of galaxies on every side. They're regions of lower density that grade into the slightly higher density of the filaments, and the still higher density of the walls, and the highest density of the clusters. The boundaries are statistical, not physical. There is no wall you could fly through, no edge you could cross, no moment at which you would pass from void to filament and feel the difference. The transition is gradual, measured in the slowly increasing frequency of galaxies as you move from the center of a void toward its edge, a frequency that is always low by the standards of the clusters, and always high by the standards of the void's interior, and that changes so slowly across such enormous distances that the concept of a boundary is almost meaningless. This gradation is important because it means that the emptiness of the universe is not a feature of specific locations. It is a property of the whole. Even in the densest regions of the cosmic web, even in the richest galaxy clusters, where hundreds or thousands of galaxies are packed into a volume a few million light-years across, the space between the galaxies is still, by any physical measure, an almost perfect vacuum. The density of matter in a galaxy cluster is higher than the cosmic average, but it is still extraordinarily low by any standard that the word density implies in everyday experience. The universe does not have dense regions and empty regions in the way that a sponge has solid regions and holes. It has regions of extreme emptiness and regions of slightly less extreme emptiness, with the matter concentrated in the least empty regions in a pattern that looks from a distance like structure, but that is up close almost entirely void. This is the texture of reality at the largest scales. Not solid and empty, not full and hollow, but a continuous gradient of near-nothingness, with the matter arranged in the thinnest possible traces along the gravitational contours of a dark matter scaffolding that is itself mostly empty space. The universe is not a place with things in it. It is a geometry with occasional concentrations of matter at the intersections of its invisible structure, and those concentrations are so sparse and so separated that the geometry, the space itself, is the dominant reality, and the matter is the footnote, and the geometry is changing. This is the fact that the expansion makes unavoidable, the fact that dark energy makes permanent. The geometry of the universe is not fixed. It is not a static container in which the matter moves and the structure evolves. It is a dynamic thing, a spacetime that stretches and curves and expands, and the expansion is not uniform in its effects. On the scales of gravitationally bound systems, galaxies, clusters, the local group, the expansion is negligible. Gravity holds these systems together against the stretching of space, and they remain bound, their internal dynamics governed by the gravitational interactions of their members rather than by the cosmological expansion. But on the scales beyond the bound systems, on the scales of the filaments and the voids and the superclusters, the expansion dominates. Space is stretching. The distances are growing. The geometry is becoming, on the largest scales, more and more like the geometry of an empty universe, a universe in which the matter is so dilute and so separated that its gravitational influence on the large-scale structure is negligible, and the expansion proceeds as if the matter were not there at all. The universe is, in this sense, approaching its own idealization. The idealized cosmological models, The solutions to Einstein's field equations that describe a perfectly uniform, perfectly isotropic universe with no structure are not accurate descriptions of the universe we observe, because the universe we observe has structure, the cosmic web, the galaxies, the clusters, the voids. But as the expansion continues, as the structure is diluted and separated and carried beyond the horizon, the universe will become more and more like those idealized models. The structure will not disappear, the gravitationally bound systems will remain, but it will become irrelevant to the large-scale geometry, which will be dominated by the expansion and by the dark energy that drives it. The universe will become, on the largest scales, what the simplest cosmological models always assumed it was: a nearly uniform, nearly featureless expanding geometry, with the matter reduced to a negligible perturbation on the smooth background of spacetime. But it goes deeper, because the expansion is not only changing the geometry of the universe, it is changing the physics of what is possible within it. As the universe expands and the average density of matter and radiation decreases, the physical processes that depend on density, the collisions between particles, the formation of structures, the ignition of stars, the chemistry of planetary atmospheres, become less frequent, less energetic, and eventually impossible. The universe is not only becoming emptier in the sense of containing less matter per unit volume, it is becoming less active, less dynamic, less capable of the kind of rapid energetic processes that characterize the current era. The expansion is not just a geometric fact, it is a physical constraint, and it tightens with every passing moment. Consider the process of star formation. Stars form when a cloud of gas, mostly hydrogen and helium, with traces of heavier elements, becomes dense enough and cold enough that gravity can overcome the thermal pressure of the gas and cause it to collapse. The collapse heats the gas, and if the density and temperature at the center of the collapsing cloud reach the threshold for nuclear fusion, a star ignites. This process requires a supply of cold, dense gas, and it requires the gas to be able to cool, to radiate away the heat generated by the collapse, efficiently enough that gravity can win. In the current universe, the interstellar medium of galaxies contains enough cold gas, and the cooling processes are efficient enough, that star formation proceeds at a rate that, while declining from its peak billions of years ago, is still significant. New stars are being born in galaxies throughout the observable universe right now as you read this, but the supply of cold gas is finite. Stars consume it. When a star forms and burns its hydrogen, it converts that hydrogen into helium and heavier elements, and when it dies, it returns some of that material to the interstellar medium, but not all of it. Some fraction is locked up in the stellar remnant, the white dwarf, the neutron star, the black hole. Over time, the fraction of a galaxy's mass that is locked in remnants increases, and the fraction available for new star formation decreases. The gas reservoir is being depleted, slowly but irreversibly, and the rate of star formation declines as the reservoir shrinks. This is already happening. The universe's star formation rate peaked roughly 10 billion years ago and has been declining ever since. The universe is not in the middle of its stellar life. It is past the middle on the descending slope, moving toward the era when the gas is gone and the last stars are burning on the last of the available fuel. The last stars to form will be the smallest ones, red dwarf stars, stars with masses between about 8% and 50% of the sun's mass. Burn their hydrogen so slowly and so efficiently that they can shine for trillions of years. The smallest red dwarfs, with masses near the lower limit for hydrogen fusion, will burn for perhaps 10 trillion years, roughly 1,000 times the current age of the universe. They are the embers of the stellar era, the last fires to go out, and they will burn long after the sun has become a white dwarf, and the Milky Way has merged with Andromeda, and the resulting galaxy has aged into a quiet elliptical populated mostly by old, cool stars and their remnants. The red dwarfs will outlast everything else that shines, and when they finally exhaust their fuel and cool to darkness, the stelliferous era will be over. The universe will have no more fires to light. What follows is a period of cosmic history so long and so dark that it has no analogy in human experience or imagination. The universe will be populated by the remnants of stars, white dwarfs cooling toward black dwarfs, neutron stars spinning down and cooling, black holes growing slowly by absorbing whatever matter comes within their gravitational reach, and by the dark matter halos that surround the remnants of galaxies, and by the faint, cold radiation of the cosmic background, still expanding, still cooling, still moving toward the thermal equilibrium that the second law demands. There will be no new stars. There will be no new planets. There will be no new chemistry of the kind that drives biology. The universe will be a place of cold remnants and dark matter and expanding geometry, and it will remain that way for timescales that make the current age of the universe look like the first heartbeat of a very long life. During this era, the degenerate era, as some cosmologists call it, the dominant structures in the universe will be the white dwarfs and neutron stars and black holes that are the remnants of the stellar age. White dwarfs will cool slowly, radiating the thermal energy stored in their interiors, becoming dimmer and redder over billions of years, eventually fading to the temperature of the surrounding space and becoming black dwarfs, cold, dark, inert masses of crystallized carbon and oxygen, invisible against the background of the universe. Neutron stars will spin down as they radiate their rotational energy, their magnetic fields decaying over time, their surfaces cooling from the brilliant X-ray emitters they are in their youth to cold, dark spheres of degenerate matter, detectable only by their gravitational influence. Black holes will grow slowly, by absorbing the occasional particle or photon that crosses their event horizons, and by merging with other black holes when the random motions of remnants in the dark remnants of galaxies bring them close enough for gravitational capture. And then, on timescales so vast that they require a different relationship with numbers than the one we use for everyday quantities, the black holes will begin to evaporate. The Hawking radiation that slowly drains their mass energy into the surrounding space is so faint for large black holes that it is completely negligible compared to the rate at which they absorb radiation from the cosmic background. But as the universe expands and the cosmic background cools, the temperature of the background will eventually fall below the Hawking temperature of even the largest black holes, and at that point the evaporation will begin to dominate. The black holes will lose mass, slowly at first and then faster as they shrink and their Hawking temperature rises, until they reach the final stages of evaporation, a brief, intense burst of radiation, as the last of their mass energy is converted into particles and photons and released into the expanding void. The evaporation of the last supermassive black hole will be, in a sense, the last significant event in the universe's history. Not the last event. Quantum fluctuations will continue to occur and the expanding universe will continue to evolve, but the last event of any macroscopic significance, the last moment when a concentrated mass energy releases itself into the surrounding space in a way that could, in principle, be detected by an observer. After that, the universe will be a place of photons and electrons and positrons and neutrinos and other stable particles, all of them moving apart from each other at the speed of light or close to it, all of them separated by distances so vast that the probability of any two of them ever interacting again is, for all practical purposes, zero. The universe will be, in the most complete sense possible, a place where nothing happens. Not because events are forbidden, but because the conditions for events, the proximity of particles, the availability of energy gradients, the existence of structures that can interact, will have been erased by the expansion and the entropy. This is the heat death, not a dramatic end, not a collapse or an explosion, but a state of such complete uniformity and such extreme dilution that the concept of change becomes meaningless. A universe in which the temperature everywhere is the same, not zero, but so close to zero that the distinction is irrelevant, and in which the matter is so dispersed that interactions are not merely rare, but effectively impossible. A universe that has arrived after an almost infinite journey at the state of maximum entropy, the state from which no further increase is possible, because there are no more gradients to erase, no more structures to dissolve, no more energy to spread. A universe that is, in the most complete sense, done. But here's the thing about the heat death that is most difficult to hold in the mind. It is not a future state that the universe will reach and then stop. It is a future state that the universe will approach asymptotically, getting closer and closer without ever quite arriving, because the approach to maximum entropy is itself a process that takes infinite time. The universe will not reach heat death at a specific moment. It will spend an infinite future becoming more and more like heat death, approaching the limit without crossing it, in the same way that a mathematical function can approach a value without ever reaching it. The universe's future is not a destination, it is a direction, and the direction is toward a state of such complete uniformity and such extreme dilution that the difference between it and nothing is a matter of definition rather than physics. And this is where the story of the universe's emptiness reaches its deepest level. Because the heat death is not only the end of structure and complexity in life, it is the end of time in any meaningful sense. Time, as we experience it, is defined by change, by the difference between one moment and the next, by the arrow that runs from the past to the future, by the sequence of events that gives the universe its history. In a state of maximum entropy, where no gradients exist and no events occur, the concept of time does not disappear in a mathematical sense. The equations of physics still contain a time variable, but it becomes meaningless in a physical sense. There is no before and after in a universe where nothing changes. There is no sequence of events to define a direction. There is no arrow of time, because the arrow of time is defined by the increase of entropy, and entropy cannot increase beyond its maximum. The universe will not end. It will simply stop having a story. The absence of story is, perhaps, the most alien concept in this entire journey. We are creatures of narrative. We understand the world through sequences of events, through causes and effects, through the before and after that give meaning to the present. The universe in its current state has a story, a history that runs from the Big Bang through the formation of galaxies and stars and planets and life, through the current moment, and forward into the future of expansion and entropy and fading. That story is not a human story. It does not have a protagonist or a moral or a resolution in any human sense, but it has a direction, and it has events, and it has the kind of structure that makes it possible to say that one moment is different from another, that the universe at one time is distinguishable from the universe at another time. That structure, the structure of change, of difference, of event, is what makes the universe a place where things happen, rather than a place where things simply are. The heat death erases that structure. It converts the universe from a place where things happen into a place where things are, or rather into a place where almost nothing is, and what is does not change. It is the universe arriving at a state of such complete sameness that the concept of a moment, of a specific configuration of the universe at a specific time, loses its meaning, because all moments are the same. The universe will not end with a bang or a whimper. It will end with a silence so complete that the word silence is inadequate, because silence implies the absence of sound in a place where sound could exist. The silence of the heat death is the absence of event in a place where event has become impossible. It is not a quiet universe. It is a universe that has forgotten how to be anything other than quiet, but it goes deeper still, because the heat death, disturbing as it is not the only possible fate for the universe. It is the fate predicted by the standard cosmological model, based on the current measured value of the cosmological constant, and the assumption that dark energy remains constant over time. But dark energy is not understood at a fundamental level. Its effect is measured, but its nature is not known. And if dark energy is not a constant, if it changes over time, if it grows stronger or weaker as the universe ages, then the fate of the universe may be different from the heat death scenario. It may be worse. One possibility, sometimes called the Big Rip, arises if dark energy grows stronger over time, if the effective pressure driving the expansion increases rather than remaining constant. In this scenario, the expansion does not merely carry unbound galaxies beyond the horizon. It eventually becomes strong enough to overcome gravity on smaller and smaller scales, tearing apart first the galaxy clusters, then the galaxies themselves, then the solar systems, then the planets, then the atoms, until the fabric of spacetime is stretched so violently that all structure is destroyed in a finite time. The Big Rip is not the leading scenario. The current data is more consistent with a constant dark energy than with a growing one, but it is not ruled out. The uncertainty in the nature of dark energy is large enough that the Big Rip remains a physical possibility, and the fact that it remains possible is itself a statement about how little we understand the dominant component of the universe's energy content. Another possibility, sometimes called the Big Freeze in a different sense from the heat death, involves a dark energy that weakens over time, eventually allowing gravity to slow and reverse the expansion. In this scenario, the universe would eventually stop expanding and begin to contract, the galaxies moving back toward each other, the cosmic web collapsing inward, the temperature and density rising as the universe compresses, until the conditions of the Big Bang are approached again in a big crunch, a final singularity in which all matter and energy are compressed to infinite density. This scenario is also not favored by current data, which shows no sign of the expansion slowing, but it is not impossible. And the fact that it is not impossible is a reminder that the future of the universe is not known with certainty. It is predicted, based on current measurements and current models, but the predictions rest on assumptions about the nature of dark energy that have not been verified at a fundamental level. The honest position, the position that the science actually supports, is that the universe's ultimate fate is uncertain in its details, but that the broad direction is clear. The universe is expanding, the expansion is accelerating, the entropy is increasing, the stars are aging, The conditions for life and complexity are temporary, whatever the ultimate fate, heat death, big rip, big crunch, or something not yet imagined. The universe is moving away from the conditions that characterize the current era and toward conditions that are less structured, less energetic, less capable of supporting the kind of complexity that produces observers. The direction is clear even if the destination is not, and the direction is not toward more, it is toward less. Less structure, less energy, less contrast, less event, less difference. Less of everything that makes the universe a place where things happen and minds can form and questions can be asked. The universe is not running down in the sense of a machine losing power. It is running down in the sense of a gradient erasing itself. The difference between the hot and the cold, the dense and the sparse, the bright and the dark, slowly and irreversibly diminishing as the energy spreads and the expansion continues, and the entropy does its patient, inevitable work. The universe is becoming more like itself, more like the uniform, featureless, maximum entropy state that the second law has always been pointing it toward, and in doing so, it is becoming less like the place where we exist, less like the brief and exceptional era of stars and planets and life that we inhabit. There is a particular quality to this realization that is different from the ordinary experience of learning something disturbing. When you learn something disturbing about the world, about history, about human nature, about the fragility of the systems that sustain civilization, the disturbance is located in the human domain. It is about things that humans did or might do, about failures of the systems that humans built, about the gap between what we hoped for and what we got. The disturbance of the universe's fate is different. It is not located in the human domain. It is not about failure or mistake or the gap between hope and reality. It is about the nature of reality itself, about the physical laws that govern the universe, about the direction that those laws impose on the evolution of everything that exists, about the fact that the universe is not a place that was built for permanence or for life, or for the persistence of complexity. The disturbance is not that the universe is hostile. Hostility implies intention, implies a universe that is working against something, that has a preference for the absence of life or the destruction of structure. The universe has no such preference. It has no preferences at all. It has laws, and those laws have consequences, and the consequences include the eventual fading of everything that the current era has produced. The disturbance is not hostility, it is indifference, and indifference, when it operates at the scale of the universe and across the time scales of cosmic history, is more disturbing than hostility, because hostility can be resisted, and indifference cannot. You cannot argue with the second law. You cannot negotiate with the expansion. You cannot appeal to the cosmological constant. The universe does not care that you are here, and it does not care that you will not always be here, and it does not care that the conditions that made you possible are temporary. It simply continues, expanding and cooling and aging in the direction that physics has always pointed it. And yet here you are, here we are, in the middle of the indifference, in the brief bright window of the stelliferous era, on a planet warmed by a star that has been burning for 4-6 billion years and will burn for roughly 5 billion more, in a galaxy that is one of 2 trillion, in a universe that is mostly void and mostly dark and mostly expanding away from itself. Here, in this improbable location, in this temporary window, matter has organized itself into something that can look up at the night sky and feel the weight of what it sees, not the weight of the stars. The stars are too far away to exert any gravitational influence on you. The weight of the knowledge, the weight of the understanding that the sky is not full, that the universe is not warm, that the conditions that produced you are not permanent, and that the universe will continue long after the last trace of your existence has been dispersed into the expanding dark. That weight is not a burden imposed by the universe. The universe does not impose burdens. It simply is. The weight is a consequence of being the kind of thing that understands, of being a mind in a universe that did not require minds, that does not need minds, that will continue without minds, for a duration that makes the entire history of life on Earth look like a rounding error. The weight is the weight of consciousness in a cosmos that is, at its deepest level, unconscious. The weight of meaning in a universe that does not produce meaning, only matter and energy and the laws that govern their interaction. The weight of the question in a universe that does not answer. There is a measurement that cosmologists make, called the cosmological constant, denoted in the equations by the Greek letter lambda. It is a single number, a value that appears in Einstein's field equations of general relativity, and that quantifies the energy density of empty space. Its measured value is extraordinarily small by the standards of particle physics, so small that explaining why it has the value it does, rather than a value many orders of magnitude larger or exactly zero, is one of the deepest unsolved problems in theoretical physics. The discrepancy between the value predicted by quantum field theory and the value observed in the expansion history of the universe is so large that it has been called the worst prediction in the history of science. And yet that small, mysterious, theoretically inexplicable number is the dominant driver of the universe's future. It is the number that determines how fast the expansion accelerates, how quickly the distant galaxies recede beyond the horizon, how rapidly the observable universe shrinks relative to the total. A single number, not understood at a fundamental level, is writing the future of the cosmos. This is not a minor gap in our knowledge. It is a gap at the center of our knowledge, a hole in the foundation of the most successful physical theory ever constructed. General relativity describes the large-scale structure and evolution of the universe with extraordinary precision. It predicted the expansion of the universe before it was observed. It predicted the bending of light by gravity, the existence of black holes, the rippling of spacetime in gravitational waves. It is a theory of almost incomprehensible power and elegance, and at its heart, in the term that governs the universe's ultimate fate, sits a number that the theory cannot explain. We know what it does. We do not know what it is, and what it does is determine the shape of everything that will ever happen in the universe from now until the end of time. The discomfort of this situation is not merely intellectual, it is existential in a precise sense. The fate of the universe, the question of whether it ends in heat death or big rip or something else entirely, depends on the behavior of dark energy over cosmic time, and the behavior of dark energy over cosmic time is not known. The current measurements are consistent with a constant dark energy, with a cosmological constant that does not change as the universe ages. But the measurements have uncertainties, and those uncertainties are large enough to accommodate a range of behaviors. Dark energy might be constant, it might be slowly increasing, it might be slowly decreasing, it might oscillate, it might change in ways that no current model anticipates. We do not know, because we do not understand what dark energy is, and without understanding what it is, we cannot predict with certainty what it will do. What we can say is that the universe's fate is being written by something we cannot see, cannot touch, cannot explain, and cannot predict with certainty. The dominant component of the universe's energy content, the thing that makes up roughly 68% of everything, is a mystery. Not a mystery in the sense of something that is merely unknown, waiting to be discovered by the next generation of telescopes or the next breakthrough in theoretical physics. A mystery in the sense of something that resists every framework we have for understanding physical reality, that sits at the intersection of general relativity and quantum mechanics, in a place where those two theories, the two most successful frameworks in the history of physics, are known to be incomplete and possibly incompatible. Dark energy is not a gap in our knowledge that will be filled by more data. It is a signal that our knowledge has a boundary, and that the boundary is located precisely at the point where the universe's future is determined. And dark matter is no different in this respect. The invisible scaffolding that shapes the cosmic web, that determines where galaxies form and how they cluster, that accounts for roughly 27% of the universe's total mass energy content, it remains unidentified at the particle level. Decades of experiments designed to detect dark matter particles directly by looking for the rare interactions between dark matter and ordinary matter in underground detectors have produced no confirmed detection. Experiments at particle accelerators designed to produce dark matter particles in high-energy collisions have found no evidence of them. Astronomical observations have constrained the properties of dark matter, its mass range, its interaction cross-sections, its distribution in galaxies and clusters, but have not identified what it is. The most popular theoretical candidates, the weakly interacting massive particles that were predicted by supersymmetric extensions of the standard model of particle physics, have not been found despite extensive searches. Dark matter is real. Its gravitational effects are measured and consistent and undeniable, but its nature is unknown. So here is the picture that emerges when you step back and look at the universe as a whole, as a physical system described by the best science we have. The universe is approximately 68% dark energy, 27% dark matter, and 5% ordinary matter. Of that 5% of ordinary matter, only a fraction is in stars. The rest is in gas and dust and the diffuse intergalactic medium. Of the matter in stars, only a tiny fraction is in planets. Of the matter in planets, Only a negligible fraction is in living things. Of the matter in living things, only an infinitesimal fraction is in minds capable of asking what the universe is made of. The universe is, by mass energy content, approximately 95% things we do not understand, and the remaining 5% is mostly gas and dust, with the stars and planets and life and minds constituting a rounding error on a rounding error. This is not a statement about the importance of minds or the value of consciousness. It is a statement about proportion, about the relationship between what the universe is and what we are within it. We are not at the center of the universe. That much has been known since Copernicus. We are not at a special location in the universe. That much has been known since the development of the cosmological principle. We are not made of the dominant material of the universe. That much has been known since the discovery of dark matter and dark energy. We are a trace element in a cosmos that is mostly composed of things we cannot see and do not understand, arranged in a structure that is mostly void, expanding under the influence of a force whose nature is unknown, toward a future that is uncertain in its details but clear in its direction. But it goes deeper, because the question of what we are in the universe is not only a question of proportion or location or composition, it is a question of duration. And the question of duration, when examined carefully, is perhaps the most unsettling of all. The universe is approximately 13.8 billion years old. Modern humans, Homo sapiens, the species that builds telescopes and writes equations and asks what the universe is made of, have existed for roughly 300,000 years. That is approximately 0.002% of the current age of the universe. And the current age of the universe is, as we have seen, a negligible fraction of the total duration of the universe's existence. The stelliferous era will last perhaps 100 trillion years. The degenerate era will last far longer. The black hole era will last longer still. The approach to heat death will continue for timescales that make all of these look small. The total duration of the universe's existence, if it ends in heat death, is effectively infinite, or at least so large that the difference between it and infinite is irrelevant for any practical purpose. Against that duration, the existence of minds, of any minds, not just human minds, but any form of consciousness or intelligence that the universe has produced or will produce, is a vanishingly brief episode. Not brief in the sense of being short-lived by human standards, but brief in the sense of being confined to a window that is, relative to the total duration of the universe, essentially instantaneous. The conditions that allow minds to exist, the availability of energy gradients, the existence of stars and planets, the presence of the right chemistry, are conditions that characterize the stelliferous era, and the stelliferous era is a phase, not a permanent state. When it ends, the conditions for minds end with it, and the universe will continue, for a duration that dwarfs the stelliferous era, by factors that resist description, in a state that cannot produce minds and does not require them. The universe does not need observers. This is perhaps the simplest and most complete statement of what the science reveals. The universe does not need observers to exist, to evolve, to expand, to age, to approach heat death. It does not need minds to give it meaning or to record its history or to bear witness to its processes. It existed for billions of years before any mind arose within it, and it will exist for an effectively infinite duration after the last mind has faded. The minds are not the point. They are not the purpose. They are not even a significant feature of the universe's history, when that history is viewed at the scale of the universe's total duration. They are a brief, local, temporary phenomenon, a consequence of the particular conditions that exist in the stelliferous era, in the thin margins of the cosmic web, on the rare planets that orbit the rare stars that have the right properties to support the right chemistry. And yet the minds are the only things in the universe that know any of this. The only things that have measured the expansion rate and calculated the cosmological constant and mapped the cosmic web and predicted the heat death. The only things that have looked at the universe and understood, even partially, what it is and what it is doing. The universe does not know its own age. It does not know its own composition. It does not know that it is expanding, or that the expansion is accelerating, or that the distant galaxies are receding beyond the horizon. It does not know that the stars are temporary, or that the entropy is increasing, or that the future is dark. Only the minds know these things, and the minds are temporary. This creates a situation that has no precedent in human experience and no comfortable resolution. The universe has, through the operation of its own physical laws, produced entities capable of understanding those laws, capable of reading the universe's history in the light of distant galaxies, of inferring the universe's composition from the motion of stars, of predicting the universe's future, from the measured value of the cosmological constant, and those entities exist for a duration that is, relative to the universe's total history, so brief that it barely registers. The universe has produced briefly and locally the capacity for self-knowledge, and then it will take that capacity away, not through any act of destruction, but through the simple operation of the same physical laws that produced it. The entropy will increase, the stars will fade, the conditions for minds will disappear, and the universe will continue, unknowing, in the dark. There is a word for the feeling this produces, though the word is inadequate to the scale of what it describes. The word is vertigo, not the physical sensation of losing your balance, but the cognitive sensation of losing your footing in a conceptual landscape, of realizing that the ground you were standing on is not where you thought it was, that the scale of things is different from what you assumed, that the relationship between you and the universe is not the relationship you were implicitly imagining. The vertigo of cosmic scale is not new. It has been felt by everyone who has seriously contemplated the size of the universe, the age of the universe, the number of stars and galaxies, but the vertigo of cosmic duration, of cosmic composition, of cosmic fate, the vertigo of understanding not just how large the universe is, but how temporary the conditions for understanding are, that is a different and deeper sensation. It is the vertigo of realizing that the capacity to feel vertigo is itself a temporary feature of a universe that will continue, indifferent and unknowing, long after the last vertigo has been felt. Look at the night sky one more time, not with the eyes of someone who sees stars and feels wonder at their number and their distance. Look with the eyes of someone who has followed this journey to its end, who has traced the emptiness from the spaces between stars to the spaces between galaxies, to the cosmic voids, to the invisible dark matter scaffolding, to the accelerating expansion, to the closing horizons, to the fading stars, to the heat death. Look with eyes that know that the darkness between the stars is not background but dominant fact, that the light is not the universe but the exception, that the sky you are looking at is a temporary configuration of a universe that was mostly dark before you were born and will be mostly dark long after you are gone. What you see has not changed. The stars are still there. The darkness is still there. The photons are still arriving at your retina from distances measured in light years, carrying the ancient light of fires that burned before your planet existed. The sky is the same sky it has always been, but what you know about it has changed, and knowledge changes the thing known, not the physical thing, not the stars or the darkness or the expanding geometry of space-time, but the relationship between the observer and the observed. The sky you look at now is not the sky you looked at before this journey began. It is the same collection of photons, but it is a different experience, because you are carrying with you the weight of what those photons represent, the thin, temporary, improbable exceptions in a universe that is mostly nothing, mostly dark, mostly expanding away from itself, mostly indifferent to the existence of the eyes that are looking at it. The cosmic web stretches across the observable universe in its filaments and walls and voids, and the voids are the majority, and the filaments are thin, and the galaxies along the filaments are separated by millions of light years, and the stars within the galaxies are separated by light years, and the planets around the stars are separated by light minutes, and the life on the planets is separated from everything else in the universe by distances so large that the concept of connection barely applies. You are here, on this planet, in this solar system, in this galaxy, in this filament of the cosmic web, in this brief window of the stelliferous era, and the universe extends around you in every direction for 46 billion light years, and almost all of it is empty, and almost all of it is dark, and almost all of it is moving away from you at speeds that will eventually carry it beyond the reach of any signal you could send. The expansion does not care about the direction it is carrying things. It carries the galaxies away from each other with the same indifference with which gravity pulls them together in the bound systems. The dark energy does not prefer the void over the cluster. The entropy does not prefer the cold over the warm. These are not preferences. They are tendencies, statistical and physical tendencies that operate at every scale and in every location, that have been operating since the first moments of the universe's existence, and that will continue operating until the last moment of the universe's meaningful history. They are the universe being what it is, doing what it does, moving in the direction that its laws have always pointed it. And the direction, followed to its end, leads here, to a universe of maximum entropy, of minimum structure, of zero gradient, of no event. A universe that has spent its entire history moving toward this state, that has produced along the way the brief and improbable exceptions of stars and planets and life and minds. and that will continue moving toward this state long after those exceptions have faded. A universe that is not hostile and not friendly and not indifferent in the way that a person can be indifferent. Not indifferent as a choice or an attitude, but indifferent in the way that a physical law is indifferent, which is to say, completely, structurally, and without the possibility of being otherwise. The stars you see tonight will burn for billions of years. The galaxy you live in will persist for trillions. The universe will continue for a duration that has no meaningful upper bound. None of this is ending soon. None of this is a crisis in any timescale that human civilization can contemplate. The sun will rise tomorrow. The seasons will continue. The Earth will orbit. The Milky Way will rotate. The cosmic web will hold its shape for billions of years before the expansion begins to dissolve its largest structures. The universe is not ending. It is continuing. And that continuation, that patient, indifferent, entropy-driven continuation, is precisely what is disturbing about it. Not that it ends, but that it continues. Not that it destroys, but that it persists, expanding and cooling and aging, long past the point where anything we would recognize as meaningful can exist within it. There is a particular image that captures something of this, though no image can fully contain it. Imagine a single photon, a particle of light, emitted by a star in a distant galaxy, a galaxy so far away that the light has been traveling for billions of years to reach the edge of our observable universe. That photon is moving through space at the speed of light, as all photons do, and as it moves, the space it is moving through is expanding, stretching the wavelength of the photon, reducing its energy, shifting its color from the blue of its origin toward the red of its journey. By the time it reaches us, if the expansion has not carried its source beyond our horizon before the photon arrives, it will be a different photon in every measurable sense except its identity. Its wavelength will be longer, its energy will be lower, its color will be shifted, it will carry, in its redshift, the record of the expansion it has traveled through, the history of the universe written in the stretching of its wavelength. That photon is a message, not a message in the sense of something intended, not a signal sent by a mind to another mind, but a message in the physical sense, a carrier of information about the state of the universe at the moment and place of its emission. It carries information about the temperature of the star that emitted it, about the composition of the gas it passed through, about the expansion history of the universe it traveled through. It is a record, encoded in the properties of a single particle of light, of a specific moment in the history of a specific place in the cosmos, and when it arrives at a detector, when it is absorbed by an atom in a telescope mirror, or a photographic plate or a digital sensor, that record is read, and the information it carries is extracted, and for a moment, the universe knows something about itself that it did not know before. But the photon is also a measure of the distance between the knowing and the known. The star that emitted it is billions of light years away. The moment of emission is billions of years in the past. The star may no longer exist. The galaxy it belongs to may have changed beyond recognition. The information the photon carries is not current information. It is ancient information, a record of a past state of a distant place arriving now because the speed of light is finite and the universe is large. The universe is not showing us itself. It is showing us its past, filtered through the expansion that has stretched the photon's wavelength and reduced its energy. And the past it is showing us is not the whole past. It is the past of the regions close enough and bright enough to have sent light that has had time to reach us. The rest of the universe's past is beyond our horizon, inaccessible, unknown, and becoming more so with every moment that the expansion continues. This is the condition of knowledge in the universe, not the condition of human knowledge, limited by the imperfections of human minds and the incompleteness of human science, but the condition of knowledge as a physical phenomenon, as a process that requires the transmission of information across space and time, and that is therefore subject to the constraints imposed by the speed of light and the expansion of the universe. Knowledge, in the universe, is always local. It is always about the past. It is always incomplete. And it is always temporary, because the observers that hold it are temporary, and the conditions that allow observers to exist are temporary, and the universe will continue long after the last observer has faded and the last piece of knowledge has been dispersed into the expanding dark. The night sky is a library of ancient light. Every photon that reaches your eye is a record of a past moment in a distant place, a fragment of information that has survived the journey across the expanding universe to arrive at your retina. The sky is full of these fragments, billions of them, arriving every second from every direction, carrying the histories of stars and galaxies in the early universe. And you are, in the act of looking, reading that library. You are extracting information from the universe's past, using the physical process of vision to access records that were written billions of years ago in the cores of distant stars. You are, in a very literal sense, a reader of the cosmos. But the library is closing. Not quickly, not in any timescale that human civilization will experience, but closing nonetheless. The expansion is carrying the distant galaxies beyond the horizon, removing their light from the library. The entropy is diluting the signals that remain, reducing the information content of the photons that arrive, making the records harder to read. The stars are aging, and when they die, they will stop writing new records. The library is finite, and it is shrinking, and the readers are temporary, and the universe does not care whether the library is read before it closes. It will close regardless. The expansion will continue regardless. The entropy will increase regardless. The universe does not need to be read. It does not need to be known. It simply is, and it will continue to be in the dark, long after the last reader has gone. What remains, when you have followed this journey to its end, is not a conclusion in the sense of a resolution. It is a recognition of the scale of the absence that underlies the presence, the vast, dark, expanding architecture of void and invisible matter, and accelerating geometry that constitutes the true structure of the universe, against which the stars and galaxies and planets and life are the thinnest possible trace of something that might, from a sufficient distance, be mistaken for significance. A recognition of the direction of the universe's evolution, from the low entropy past toward the high entropy future, from the concentrated to the dispersed, from the structured to the uniform, from the bright to the dark. A recognition of the temporariness of the conditions that produce the recognition itself, the brief window of the stelliferous era, the rare planet, the improbable chemistry, the temporary mind, and a recognition of the silence. Not the silence of a universe that has nothing to say, but the silence of a universe that was never speaking. The universe does not communicate. It does not signal. It does not reach out across the void to make contact with the minds that have arisen within it. It expands. It cools. It ages. It moves along the arrow of entropy toward the maximum entropy future that the second law has always pointed it toward. And the minds that have arisen within it, the brief, local, temporary exceptions that have looked up at the sky and asked what it means, are not recipients of a message. They are not the audience for a performance. They are not the purpose of a process. They are a consequence of physics, a temporary configuration of matter in a universe that will continue, indifferent and unknowing, long after the last configuration capable of asking questions has dissolved back into the expanding dark. The universe is not waiting for you. It is not waiting for anyone. It does not wait. It expands, and the expansion carries the galaxies apart, and the entropy increases, and the stars age, and the horizons close, and the darkness grows, not as a threat and not as a punishment and not as a statement about the value of the things that exist within it, but simply as the operation of physical laws that have no awareness of what they are doing and no preference for any outcome. The universe is the largest and most indifferent fact in existence, and it is mostly empty, and it is getting emptier, and the emptiness is not a background condition. It is the point. You looked up at the night sky at the beginning of this journey and saw stars. You saw light. You saw what seemed like a universe populated with burning things, a cosmos that, whatever its scale, was at least full of something. And now you know that what you were seeing was the exception, not the rule. The darkness between the stars is not the space between the things that matter. It is the thing that matters. It is the dominant fact, the overwhelming majority, the true texture of the universe at every scale, from the spaces between stars to the spaces between galaxies to the cosmic voids to the expanding geometry of spacetime itself. The light is real, but the darkness is more real. The darkness is older and larger and more permanent, and it is growing. The last stars will burn out. The last black holes will evaporate. The last photons will be stretched by the expansion to wavelengths so long that they carry no energy worth measuring. The last particles will drift apart in a universe so vast and so cold that the probability of any two of them ever meeting again is, for all practical purposes, 0. And the universe will continue in that state for a duration that has no meaningful end, expanding, cooling, unchanging in any significant sense, a geometry of near nothingness extending in every direction without limit, without event, without observer, without the possibility of being known. That is the universe. not the universe of the night sky, not the universe of the telescope images, not the universe of the popular science books with their glowing nebulae and their spiral galaxies and their sense that the cosmos is a place of beauty and wonder and inexhaustible richness. Those things are real, and they are part of the universe, but they are the smallest part, the thinnest, briefest, most improbable part. The universe, in its full extent and its full duration, is something else. It is the void between the galaxies growing wider with every moment. It is the dark matter scaffolding that cannot be seen. It is the dark energy that cannot be explained. It is the entropy that cannot be reversed. It is the horizons that cannot be crossed. It is the silence that cannot be broken, because there is no medium to carry the sound, and no one left to hear it. You are here, in the middle of it, for a moment. The moment is real. The stars above you are real. The light reaching your eyes is real, and it has traveled for years or centuries or millennia to find you, and in that sense it is the most improbable thing in the universe. A photon that survived the journey, that was not absorbed or scattered, that arrived at exactly the right place at exactly the right time to be received by exactly the right kind of matter. The improbability is real. The briefness is real. The darkness surrounding the light is real, and it is vast, and it is patient, and it is not going anywhere. It is simply waiting, not waiting in the sense of anticipating, not waiting in the sense of wanting, but waiting in the sense of persisting, of continuing, of being the thing that remains when everything else has faded. The darkness does not need the light. The void does not need the galaxies. The expanding geometry of space-time does not need the matter that moves within it. The universe does not need you, it never did, and it will continue in your absence exactly as it continued before your presence, expanding, cooling, aging, moving along the arrow of entropy toward the maximum entropy future that has always been its destination. The stars will burn for a while longer. The galaxies will drift apart. The horizons will close. The fires will go out. And the universe will be what it has always, at its deepest level, already been. Mostly nothing. Mostly dark. Mostly silent. Mostly alone. And vast beyond the reach of any word that has ever been used to describe it. Vast in a way that makes the word vast itself seem small. That makes every human concept of scale and distance and duration seem like a child's drawing of a map, that makes the night sky with all its stars and all its darkness seem like a single candle held up against the interior of a space so large that the candle's light does not reach the walls, and the walls, if they exist, are moving away from the candle, faster than the light can travel, and the candle is burning down, and the darkness is not waiting for it to go out, because the darkness does not wait, and the darkness does not watch, and the darkness does not know that the candle was ever there.